So GCSE, you learn that the electrons are arranged in shells that orbit the nucleus, and you can only contain a certain number of electrons in each shell. So the first shell, you have 2, the next shell 8, the next one 8, and so on. So this is not 100% true when we get to A level, but we can use this as a basis to get started. So what we're saying is, this is shell 1, and we'll see there are some similarities when we look at the A level model in a minute. Shell 2, and then it gets a little bit different with shell 3 and so on. Okay, so let's look at how electrons are filled in at A level. So what we have, firstly, this arrow here, that's the energy. Okay, so we're going higher in energy as we go up. And what we have down here now are the names of the places that we fill in our electrons, the shells. We've got the 1s shell, for example, then 2s subshell, 2p subshell. So what does this mean? Well, each of these boxes we'll call an orbital can completely fill up with 2 electrons. So for now, we'll represent the electrons with these arrows. Don't worry too much about what they mean, but each arrow is an electron. So that's our first shell completed. So the same way as before in GCSE, we fill in the lower energy shells first. That is the shells nearest to the nucleus. So if an atom only got a couple of electrons, it's only going to get up to here. So helium is only going to get up to here. Now, in GCSE, we said there was 2 electrons in the first shell. Well, you can see this is the first shell. Big 1 stands for the number 1, the first shell. There's 2 electrons there. Then we jump up. We have the next shell here. So we can think of it, this one here down below as the first shell, and this one as the second shell. So because we can fit 2 in every one of these little boxes, which we call orbitals, you'll notice that there's 2 there in the first shell, and since we've got in total 4 boxes here, that would be 8 electrons in the next shell. So I'll just fill them up for now, and we'll look at this in more detail later on. So we have 2 electrons in the first shell and 8 in the next shell. So far, there are similarities with the model that we learned in GCSE, but obviously there's some differences here as well. So the similarity, the first shell contains 2 electrons, the second shell contains 8. Another similarity, we fill up the electrons from the lower energy levels up to the higher energy levels. Okay, but now let's look at the kind of glaringly, obviously differences that we have here between GCSE, because you instantly look at this and a lot of students will get very confused because it looks very different and there's a lot going on. So one of the obvious differences that we have, as well as these things called shells, clearly in this second shell, there's something strange going on. We seem to have 2 kind of mini levels within this big shell, the second shell itself. Okay, so that's true. So although this is a major level down here, first shell, and these 2 kind of levels are very close to each other compared to this one, these 2 here are actually 2 subshells within this second shell. So at A level, we need to understand that in addition to shells, major shells, if we look a bit closer, we can see that the shells are sometimes, although not always, divided into what we call subshells. So although the first shell here is only really one shell, isn't divided further. This second shell, we can see, contains 2 sub-shells. Okay, so similarly, like the way you would do A-levels, you have year 12 and year 13. Okay, it's still A-level, but quite often the stuff you learn in year 12 is at a slightly lower level, slightly easier to that which you do in year 13. Okay, it's still all A-level, so still all the same level, but it can be subdivided into 2 sub-levels. Okay, or think of it like a computer game. You start at one level, let's say it's Super Mario, you're in the mushroom land, then you progress, you complete that level. Once it's filled up, you go up to the next level, but actually maybe the next level, your desert land, is divided into 2 parts. You've got the desert sandy bit outside the pyramid, and then you've got the bit inside the pyramid, both within the same level, but divided into sub-levels. Okay. Now, these different energies, although they are sub-levels, the 2s is slightly lower than the 2p, which means that you've got to complete the 2s sub-level before you can move up to the 2p. Okay. So far then, as we've seen, we've still got the 2 shells, but the shells can be subdivided into subshells. And in terms of these letters P and S, we'll look at what we mean by them in a bit more detail later on. So after the second shell, the next energy level will be the 3rd shell. So the 3rd shell itself is split up into sub-levels. We have 3s, 3p, and 3d. So we always add electrons going from the lower energy to the higher energy. So the next place for the electrons to fill up, if there is that many electrons in your element after 2p, if that's all completely filled up, have to go to 3s. So I'm going to fill in my electrons in the 3s. Okay, again, arrows representing the electrons there. After 3s, we go up into the 3p, as you can see. And that's the next energy level here. So I fill up electrons. And we'll talk more about how we fill them up in terms of these boxes, which are called orbitals, a bit later on. Okay. You'll notice the S's can only fill up 2 electrons. The P's in total have a capacity of 6. Now, you have to follow the rule in the sense of electrons fill up the next available energy level. So after 3p, although you might think you complete it with another level 3, a bit weird, in chemistry you will come up with these exceptions a lot of the time. Here's one such example. 4s, this subshell, is actually slightly lower in energy than a 3d. Okay, so we've got no choice. We've got to fill up the 4s next. That's where we would go. Okay, then once that is complete, then we can go into a 3d. But for now, let's just understand electrons filled up from the lower energies to the higher energies. This graph will show you what the next sub-level is. Yes, our main shells are sometimes or usually subdivided into subshells. Okay, and subshells themselves are comprised of orbitals. The S subshell has 1 orbital. The P subshell has these 3 orbitals, there's 3 boxes. Okay, and each orbital can fit in 2 electrons. So if we remember, the S subshells fit 2 electrons in. So that can help us to remember that the S is on the left here because it's 2 elements thick. Yeah, I've got 2 at the top as well. And then 2 on this block here. 1, 2, 1, 2, 1, 2. So 2 elements thick. That's the S block. remember the P subshell has a maximum capacity of 6 electrons, and this P block is 6 elements thick, and the D subshell can fit 10 electrons in total, and the D block is 10 elements thick. So that's a good way of remembering it. So to help us to remember the order in which we can fill in the electrons for our elements or our ions, we can divide our periodic table into these blocks. Okay, so in an exam, you'll be given a periodic table. You're free to annotate it and divide it into the blocks as follows, if you would so wish, if you have time and if that's useful for you. So there is a general pattern here that we can use to help us remember the order which we fill in the electrons for the electron arrangement. And as usual in chemistry, there's some exceptions to a general pattern which we just need to be aware of to help us to do this. So what does it mean to say it's in a certain block? So for example, if I said beryllium, now with this periodic table mapped out in blocks, if you compared it to a periodic table with the elements inside of it, beryllium would be just here. Okay, this one here, it's in the S block, which means that its outer electron is in an S block. In fact, it's in the 2s block. Okay, if we're talking about neon, now neon would be here. Okay, so its outer electron is in a P block. In fact, its outer electron is in a 2p subshell. Yeah, and I should say beryllium's outer electron is in a 2s subshell. Okay, and then for example, another one, titanium. If you found titanium on your periodic table, you'd find out that it's here, which means that it's a D block element. Its outer electron is in a D subshell. Specifically, it's in the 3D subshell. Okay. Now, in terms of filling in the electron arrangement, we will consider that now. So again, you would need to be aware of the pattern that we got here. If you look at 1, which is 1 here, and 2, 3, 4, 5, 6, 7, you'll notice for the S block, that corresponds to the period. Okay, so the first period is up here. Some people forget that the very first period only contains 2 elements, hydrogen and helium. That's the first period. Then we move on to the second one, down here with lithium. Okay, 3 and then 4, 5. So that's kind of consistent. The numbers for the different S block elements, they're consistent with the period of your elements, with the periods in the periodic table. Likewise, it's consistent for the P block as well. So this here is the second period, and this is the third period, fourth period. So this is all consistent, that makes sense, okay? Now, clearly there's no 1p though, okay? But then that space is taken up by those 2 elements. Just remember they're in the S block. Now, where the exception comes in will be the D block, which doesn't seem to map on in the same way nicely as the other ones do, because the 3D block here is actually in the 4th period, as we can see, 4s and 4p. The 3D block seems to be in the wrong place, but it's not. This is where it should be. So if you notice 3D, 4D, 5D, 6D, they're all actually, it seems to have been lowered by 1 level. So where I will remember this, D, think about it's descended, right? This entire block has descended by 1 level. And if you can just remember that, then it should be quite straightforward and simple to remember where the different subshells are as you map them out on this periodic table. And if you can do that, you can fill in electronic arrangements quite easily, especially for generally the normal atoms. So let's have a go. Let's start with beryllium, as we mentioned earlier. Now beryllium has an atomic number of 4. That means it has 4 protons. It means it also has 4 electrons. So we can fill in our subshells until we get to 4 electrons. So similar to GCSE, you fill with the lower energies and you work your way up to the higher energies, but now we've got different notation. So we're starting with 1s. Okay, that's the very first subshell to fill in. Now how many electrons can you fit in the S? Well, it's 1 electron for hydrogen, then the next one for helium. So that'd be 2, and we draw it like that, a little 2 at the top. So that's 1s2. After the 1s2, we finish the S subshell, we're going to go into the 2s. So 2s is next. Now beryllium is just here, which means that 1 electron for 2s, 2 electron for 2s. So 2s is now full, but that's the end of the electronic arrangement for beryllium. 2 plus 2 is 4, same as the atomic number, therefore it helps us to show it's right. Let's do another example. Next example, let's do neon. Okay, so neon has an atomic number of 10. That means it's got 10 protons, it also has 10 electrons. It can be found just underneath helium, so it's just the top right green square over there. Again, we fill it in the same way. So the first one is 1s, that needs to be complete with 2 electrons before we move on to the 2s. Let's be complete with 2 electrons, yeah. Then we progress over here to 2p, and as we said, it's right at the end. For neon, which means a 6, okay, each square is like another electron, so you've got 2p6 there. 2 plus 2 is 4, plus 6 is 10. As we said, we've accounted for all 10 electrons in neon. Let's do another example. Titanium. Now, titanium has an atomic number of 22, therefore has 22 electrons as well. And it's found in the D block, second one at the top of the D block there. So again, I would do 1s2. I move on to 2s2. I go on to 2p6. From 2p6, I go on to 3s2. Then 3p6 is next. After 3p, I go on to 4s. That is to be completed to 4s2. I now progress to the 3d subshell, where titanium is to be found. And I know that it's the second one there. So I'm going to fill it up with only 2. So it's not full. It's got only 2 electrons in that subshell. And if you counted all these little numbers at the top, it would equal 22. So when filling in the electrons using the box and arrow method, you will use arrows to represent the spin of the electron. So electrons can have either upward spin or downward spin. So for example, we have neon there, the first electron you draw up. Second electron you'll draw down. So think of it as electrons, same charge, spin opposite directions. Every orbital represented by these different boxes here, if they have 2 electrons inside of it, they will have opposite spins. You fill up the lower energy first before you can move on to a higher one. So 1s is filled, let's go into 2s. Spin up, spin down. Next, we have to go into the 2p subshell. I'll fill up the first electron, first orbital, first electron there. Now, in this case, all of this subshell has the same energy, but electrons, as best they can, will want to avoid each other. So you're not going to get 2 electrons in the first orbital just yet. The next electron will want to avoid this box, avoid this orbital, so you draw the electron in the next box, the next orbital. Think of it like a bus. If you went onto a bus and there are a few people sitting in there, sitting on their chairs with empty spaces next to them, but you don't know them, you will most probably go and find an empty couple of seats for yourself. It'd be kind of weird if you sat next to someone you don't know when there's lots of empty spaces everywhere else around in the bus. In the same way, electrons will like to find their own orbital if they can help it first. So in the same subshell, but they will go to different orbitals. Once you've partially filled up each of those orbitals with one electron in each one, then and only then you go back to the first original orbital within that subshell, and you can then add that electron. Then the next one would be the next box, and so on, like so. Let's give another example with titanium, filling in the electrons in the same way. So the first 1s orbital, arrow up, arrow down. Then I move on to the higher level. Up, down. Then I move on to the higher level. Again with the 2p, I put an electron in the first orbital. I then go to the next orbital, electron up, the next orbital, avoiding each other as best they can. Now they can't help it. I go back to the first orbital, arrow down, next orbital, arrow down, final orbital in 2p, arrow down. Then I can move on to 3s, arrow up and arrow down. Then 3p6, or 3p, first orbital, then the next one, avoiding each other, these electrons as best they can. Then they're forced to go back to the first orbital again, then the second, then the third. 4s, up and down, that's 4s2. Then they move on to 3d. So for 3d, one electron in the first orbital, again they avoid, so you go to the next one, like so. So when you write out the electronic arrangement for ions, it's a very similar idea as for the atoms. So this is beryllium 2+. So therefore it's lost 2 electrons. So that's the normal beryllium structure, 1s2, 2s2. Since it's lost 2 electrons, we no longer need the 2s2 there. So it's going to just be 1s2. For this example, fluorine, normally it's 1s2, 2s2, 2p5, but for the fluoride ion, it has now gained 1 electron. So we're going to add an electron into our structure. It's going to be 1s2, 2s2, and instead of 2p5, it's going to be 2p6. Okay, so a couple of exceptions to the normal rules. If you look at the transition metals on the first row, 2 elements which fill in their orbitals and their subshells a little bit differently are chromium and copper. So they both begin with C, help you to remember them. So to see what the issue is, I've got here the previous element so we can compare what actually is different about chromium and copper. So vanadium, for example, is filled in the normal way, and I've written out the electronic arrangement here. After vanadium then, it's chromium. So we may expect, just looking at vanadium structure, you want to add one more electron to it. Therefore, instead of 3d3, you may expect it to be 3d4. However, what actually happens instead is what we end up with is 3d5, black pen, 3d5, and this is 4s1 instead of 4s2. So what's happened is one of the electrons from the 4s subshell has gone up into the 3d subshell. So as I say, this is not the normal way it happens, but for chromium is one of the exceptions. We get this exceptional result. So how that would look like if you had the boxes and the arrows would be like this. So you can see the arrangement now leads to the 3D subshell being half full. And a half full D subshell is more stable than one that is, let's say, got 4 or 6 electrons within it. So this arrangement is actually a more stable arrangement for chromium, hence why one of the electrons is promoted in this situation. The other example of the exception is copper. Again, I've compared copper with its previous element in the periodic table, which is nickel. So we would expect, if we go one more electron from nickel, the arrangement to be 4s2 3d9 for copper. Again, that's not exactly what happens. So again, we're going to get the situation where one of the electrons from the 4s is promoted, added to the 3d subshell. So we add one electron plus one electron from 4s, so that would give us a number 10 here. Yeah, because one extra electron from nickel plus one of the electrons from 4s has gone to the 3d subshell. So how that would look with the box and arrow would be one arrow in the 4s, just like we saw for chromium, and then this 3d subshell would end up being complete. So again, the reason copper does this is that it's a more stable arrangement if the 3d subshell is complete. So in the case of chromium, being half full is stable, and also in the case of copper then, being completely full for this 3d subshell is another very stable arrangement, more stable than the arrangement you may have expected, which would have been 4s2 3d9. That doesn't happen. We get 4s1 3d10, more stable. Hence, learn the exceptions. Both begin with C, chromium and copper. Another strange thing about transition metal is that when they form ions, you need to remove from the 4s subshell before the 3d subshell. So in the case of this example, you have iron, and you've got an iron, 3+. So I'm going to remove 3 electrons from the above arrangement, which means, as I said, I'm going to remove from the 4s first, and then since there's 2 electrons there, I'm going to remove those 2, and I have to remove one more because I'm making a 3+ ion, so I'll remove one from there as well. So 4s is gone, so I can make that basically invisible here, and then put the 3d as having removed 1, it becomes 5. So a bit strange there when it comes to transition metals. Just remember that you remove the 4s from the 4s subshell first before you move on to the 3d and remove from there. So there is a shorthand way of writing out the electronic arrangement for some elements. Look at the top one, that's calcium. That's its electronic arrangement. Look at the bottom one here, that's argon. Now you'll notice that argon's electronic arrangement can be found within calcium. It's everything up to here. So we can use this fact to help us to write out a shorthand way for calcium. So it would look like this. Calcium, its structure is the same as argon. I'll do it in a square bracket like that. It's the same as argon up to here with the addition of the 4s2. So if I write argon in the square brackets and then put 4s2 afterwards, that's the same thing as saying the electronic structure for calcium. Now, this only works for noble gases. You can't just choose any random element in the square bracket before the one you want to do. And it works for the most previous noble gas, okay? So which noble gas came most recently before the element you are interested in? And whatever that noble gas is, that's the one you can put in the square brackets, and whatever the remaining electronic arrangement is, that's what you would put after that. So what shape do we have for, say, the s orbitals? Well, they are going to be spherical, so it's like this. Say the 1s, the nucleus in the middle, you can expect to find the electrons within this space. Then you have the 2s orbital. Think S for sphere, so S, spherical shape, sphere. And then the 2s will be a larger sphere, goes around the outside. Okay, so I want to talk about the p subshell and the orbitals within the p subshell. So for example, here we have oxygen, where we have 1s2, 2s2, and then we come on to the p subshell. Obviously p is 3 orbitals and a total capacity of 6. The shape of the p orbitals is like a dumbbell. So I'm trying to illustrate this with a bit of a graph. So we can think of it as 3 dumbbells in 3 planes at right angles to each other. So for example, if we think of this orbital here, this first one, we're going to call it the x. Okay, well that's going to be a dumbbell in the x plane. So if you see this graph here, got the x-axis and the y-axis. Okay, we've even got a z-axis we'll come to in a minute. So the x-axis first, we will draw the dumbbell. Something like that. Okay, so we can expect to find electrons within maximum amount of 2 electrons within that orbital. That would be your x. So in other words, the first orbital of the p. Now remember, your first electron will go in there. The next electron wouldn't want to share with that orbital just yet. It'd want to go to the next orbital, which will be the y. Okay, so you've got the 2p, this is the y, the next one to it. Now again, looking at our graph here, that's the y-axis, just like in maths. So I'm going to draw my dumbbell now in the y plane as follows. Okay, we can get a maximum of 2 electrons there. Remember, 1 electron in the x, then the next electron, one will be in the y. Okay, they want to go to separate orbitals before they're drawn up in the same orbital when they've got no choice. Okay, so we've got the x and the y, and the last one, the hardest one to draw, would be the z. So that's this one over here. Okay, so I'm going to draw that in red now. So z is at right angles to the x and the y. Think of it as coming through the page. As I say, it's the hardest one to draw here, but you'll get the idea, I'm sure. Into the page, and this one is going, well, this one's going into the page, the other one's coming out of the page, and there we go. So we've got the x, y, and the z, 3 different planes, 3 different orbitals, like 3 different dumbbells, making up the p subshell.